Okay, so this is my little overview of regression, and this we followed up by kind of a video where I give a really simple introduction to a regression problem. But this is kind of the high level review on what we're doing with regression and what regression is. So here's the book definition of regression. It's basically a model building exercise where for standard regression, we have a dependent variable, for example, a house price, and we have one or more independent variables, which we use in this case to predict house price. So in my example, we could have a ratio variable, which is the size of the house or the size of the lot, and we could have a categorical variable, which is maybe the type of house. Is it a single family house? Is it like a two-family house? Is it a townhouse, etc.? And we can kind of divide the problem further in that we have simple regression where we have a single independent variable and multiple regression where we have more than one independent variable. So this is kind of more my definition. And basically, the commercial context, when we talk about regression models, it's basically any model with a continuous dependent variable. Now, there's lots of types of regression where there are, categorical dependent variables. That's maybe a little bit too complicated in terms of the definitions of this class. Um, but I give like four examples here. So we're predicting revenue for different product lines. For example, I think Walmart had a kind of an open sourced competition where you had to predict their sales in different product lines. And the prize for this competition is you would get a job at Walmart. I guess a high powered data science job, not like a checkout job. Predicting the points scored in an NFL game, predicting home value, whether for being a real estate agent or giving the true value of the house for taxes, or maybe predicting yield for different agricultural crops. Okay, so what I'm going to do here is give kind of two little examples. The first is a regression problem, and the second is a more kind of traditional kind of class prediction problem, just so you can kind of see the difference. So here's a regression problem. We have a continuous dependent variable y, and then we have these independent variables x1 to xk. And what we're doing is we're trying to predict the opening weekend movie revenue. So this may be for, advertising purposes, kind of how much concessions to do, etc., etc. And we're going to base this on several independent variables. So the number of screens the movie is shown on is quite important. Some measure of pre-release social media buzz. So this could be something like the average number of tweets in the week before release. We could have some measure of the star power of the movie, maybe the revenue that the major actors have gained from their previous movies. We might have the movie category. Action movies may do a little bit better than, say, romance movies. We have the movie budget because obviously that's kind of an important predictor. We're not going to spend hundreds of millions of dollars on a very niche movie that very few people are liable to see. And again, some measure of pre-release online reviews. Kind of certain people will get the movie before release, kind of major newspapers, and they will do reviews of the movie. So again, how well the movie is received pre-release. So this is the regression problem where we're predicting a continuous dependent variable. And versus a class prediction problem. So this is the other type of problem. And as I said, it's a little bit more complicated than the book would say. There's a type of regression called logistic regression where you have a categorical predictor. But let's just call this regression versus class prediction. So here, y is the categorical dependent variable, and x1 to xk are independent variables. And what we're trying to do here is predict whether a customer churns. So imagine we work for a telecommunications company and people or companies have yearly contracts. If the company does not renew their contract, then they're considered to have churned. So this churn is the opposite of renewal. And this is kind of important. if we think a customer is not going to renew, we may do some additional marketing. We may want to look at high value customers who don't renew. We may want to kind of analyze our customer service based on the outcomes of this. So does a customer churn? Yes or no? And then we've got things like the number of years you've been a customer, how much you're paying, how satisfied you are. That's going to be important. How many calls you make a year, how many texts you make a year, and how much data have you used. So basically kind of service attributes combined with some measure of satisfaction. And we might be able to predict whether, the liability, how likely it is that you're going to renew your contract or not renew your contract based on this. So regression, class prediction. So in the language of this textbook, I thought I'd put together my little movie example, because this is an area I've done some work in. So why do we use regression? Well, for descriptive analytics, we just want to analyze patterns. We want to look at, which factors are important, summarize which factors are important in movies, and kind of some measure of how they relate to movie revenue. We can maybe do some pictures of correlations and stuff like that. So we can kind of use regression as a basis of descriptive analysis. But we might actually want to predict the opening weekend movie revenue, because we might want to, again, use this to do things like set our advertising budget and set, how much we pay for concessions and things like that. And that leads us on to prescriptive analytics, where we're doing more than prediction. We've got some model for changing our marketing spend based on the results of this regression, or the number of screens based on these results. Now, as I'm going to talk about in a minute, things like this regression is not quite as simple as it seems, because there's something, and again, this is way beyond what we do in this textbook, but there's something called reverse causality here, in that we use kind of number of screens to predict revenue, but in a way, number of screens relies on revenue, because the more revenue you have, the more screens we have. So we've got something that can kind of work in both directions there. So here's a little example, and I'm not going to put the article up. And this is Amazon SageMaker. And this is just, again, we've talked a little bit how analytics now is becoming increasingly more dashboard oriented. And, it's nice to learn these techniques, but quite often a lot of the technicalities are hidden on these dashboards. And so there's quite a few online machine learning platforms. Google has an online machine learning platform. Microsoft has Azure. Amazon has SageMaker. And what they're trying to do is they're trying to make it as non-technical as possible. So you put in some data, you say what you want to predict into the cloud. And, if it's a continuous dependent variable, you would use some sort of regression model. If it's something like, churn, or whether somebody would buy a product or not, you would use some sort of a class-based kind of classification model. And so you put in your dependent variables, your independent variables, and then you would build the optimal model from a set of different models. So that's just an example of how, regression would be. And this is used here for predicting things like online shipping, things like on-time delivery and delivery time in a supply chain context. Okay, so I'll talk a little bit about kind of what we do in this chapter and some of the limitations of what we do in this chapter as to how regression is used in practice. So in this chapter, we're basically using this R-squared measure, and R-squared is the amount of variation in the data accounted for in our model. And basically, and we don't do it in a very sophisticated way in this chapter, we can look at the R-squared adjusted measure, which basically adjusts for the number of variables. Because say, for example, I'm predicting movie revenue, and I have my basic movie predictions. So I have the pre-release social media buzz, the star power. I could have maybe the season of release, the very important variables. But then I could add a load of junk to the model. I could have, what did the star have for breakfast on the day of filming? Stuff that's not relevant, really going to be noise. I can add a load of junk to the model, and the R-squared is never going to get smaller, because I can basically set the regression coefficients for the junk variables to be 0. So the R-squared adjusted basically has a penalty for the number of variables in the model. the idea, if we have the model, too much junk in the model, things like, what people had for breakfast in the model when it's not relevant, it's liable to what we call overfit the model and give poor predictive performance. And the disadvantage of how we do it in the book is that, there's like lots of different fancy types of regression. Not all of these use R-squared to measure the strength of the model. And we take these values as values of predictive power, but they're not really pure measures of predictive power. They're just showing us how well we fit the data in the training data set. And even when we adjust for the number of variables, they don't directly measure how good our model is at prediction. So what do we tend to do commercially? Well, we do something kind of holdout or out of sample validation. And again, I teach kind of in the MBA program, I teach the more advanced predictive analytics class, and I have a huge emphasis of holdout validation in my class. Though again, this is kind of the standard course I've taken over based on the textbook, and there's not much of an emphasis here. But I will go through some of the basics. But just know none of this is going to actually be on the exam. So what do I mean by holdout validation? Let's just think of it in the simplest terms. I have a set of data. So I have data from 1,000 previous movies. I split the data into training and test. So I maybe have 500 movies in my training data set and 500 movies in my test data set. I build my regression model on my training 500 movies. And then I basically predict, using my model based on the training movies, I predict the model for the test data and see how big my error is. So I would have all the actual movie revenues in the test data, the movie revenues as predicted from my training data set, and I find some measure of error. For example, I add up all the squared errors and divide by the number of movies to give me the mean squared error. Again, I'm not going to get into the technicalities here because this is out of scope of the class, but I feel it's important, so I've included it in the video. And kind of slightly more complicated here, we have something called k-fold holdout validation. And the disadvantage with the simple holdout validation is when we're building the model, we're losing 50% of the data. So the idea with k-fold validation is we want most of the data in our training data set. So we're going to split the data into k equal segments. And for each of these k segments, we basically, so say, for example, we set k equals 10. We take segment 1. I have 10% of the data. I build the model on the remaining 90% of the data, and then evaluate the model on this remaining 10%. So for each of these segments, I have some measure, I have a movie prediction based on the model from the remaining 90% of the data. So I just repeat for each of the k segments, and eventually I have some measure of kind of how accurate the model is for all of my different movies. But each of my predictions, the actual movie that I'm predicting is not included in the model building. So again, this is out of sample validation. We could go even further. We could build the model with every item except the movie we're predicting, and do this for kind of every single movie. But if it's a big data set, then this is very, very difficult in terms of computation time. So that's kind of model selection. And this is just, I took this from the textbook from my previous course. And if you want to take some of the stuff in this course a little bit further, this is it's a free textbook, and it's called Introduction to Statistical Learning. So it's like an introduction to kind of some of these data mining, data analytic techniques. And again, it's just showing holdout validation. We have a data set. This is 5-fold validation. And each time we're predicting in this holdout data, and we're building our model on the remaining 4/5 of the data. Okay, so what do we cover in this class? So we do a little bit of examining correlations between variables. We do some simple linear regression, some multiple linear regression. And we also do some interesting, we do some regression with some different functions. So example, how do we, rather than linear regression, how do we, do we compare linear regression with a quadratic function, a log function, an exponential function, which is quite fun. And then we do model selection with R-squared. Now, I'll go to the bottom at this. So a graduate student in economics, statistics, or something like that could easily take 4 or 5 semester courses in regression. And we're doing a week in regression in this class. And again, the advanced course I teach, we probably do about 3 weeks worth of regression. So, Rome was not built in a day. So we can't really cover all these techniques. This is kind of the sort of stuff you would do in, multiple semesters in a more focused graduate degree. But I can talk a little bit about some of the things that we're kind of missing out in this class, just in case you're dealing with an economist and they want to look down and you say, huh, MBA students, I'm an economist, and they start using fancy terminology. So let's just kind of get a little bit of this terminology. So first thing we cover is multi-level models. And the idea here is we kind of have a regression at a higher level and at a lower level. So say, for example, we're predicting house prices. We may want to build a model where we have variables for the specific metro area. So we may want things like, unemployment in the metro area, job creation in the metro area, things like that. But we also want kind of things on the level of the house. So we want things like the square footage, the condition of the house. That's called a multi-level regression model. We might also have this, what we call endogeneity effects. And economists absolutely love these terms. They will talk about endogeneity, exogeneity all day long, just to actually confuse you. And this is my example for this, is exactly what we had in the movie regression. The movie screens influence revenue, and then revenue influences movie screens. Now, in fact, so there's lots of kind of regressions. There's something economists would do called a two-stage SLS regression that will account for some of these effects. But in fact, the results are usually very similar to the simple regression, which we call ordinary least squares, that we cover in this class. So for business purposes, these regressions have very little difference than the general ones that you would create in this class. Now, we assume very simple effects with standard regression, i.e. we've got a dependent variable and that's influenced by independent variables. But we can get, again, what we call causal or structural regression models. So we may have like a multi-stage regression. So we've got unemployment and inflation. These things affect consumer sentiment, which again affects house prices. But again, some of these kind of complex models, there's something called structural equation models where we look at more complex causal relationships. But again, they're a little bit out of the scope of this class. We kind of did cover, I don't know why I didn't put that in. We covered regression with different functions. But sorry about that. That should have been kicked out. We didn't cover advanced statistical learning. Yeah. Okay, I made a minor change to the slides to add a different kind of method. So we have survival analysis. So these are models that we kind of predicting survival over the time. So these kind of come from physics and analogies of things like radiation decaying over time. But they're used a lot, for example, to measure dropouts. So we have, for example, if we're measuring gym membership and we have 5 people drop out after 1 month, 7 after 2 months, etc., etc. And we want to kind of, model this with relation to some demographic variables, for example, people's age, people's previous exercise habits, people's weight, etc. Then that's what we use survival analysis for. And again, we could also do it in a similar way to churn analysis, but rather than working out, do they renew a contract in any specific year, we'll look at how customers, how long the customers stay with us, when they drop out, and why they drop out. There's a lot of like advanced kind of regressions. We have local regression where we basically just fit different regression functions at different areas of the regression and then kind of smooth this out, similar for spines. We also have maybe neural network regression where we build models with neurons. So there's this wide range of advanced regression models. And in a way, if we're doing them through a dashboard, these don't look very different from regression, except they give slightly different output. but they're kind of optimized for, improving prediction on certain problems. And as I said at the beginning, a graduate course, we could easily take 4 to 5 semester courses in regression. So just being kind of aware what's available. And if you want to do some advanced stuff, where was that book? Yeah, you may want to actually check out the textbook I give you in the slides. Okay, so this now is, and this is like a little paper. I've actually got the paper up here. And this is from, basically, I just want to give a few examples of regression, uses of regression, kind of nice, simple ones. And this is from the MIT Sloan Sports Analytics Conference. And there's a lot of controversy in sports as to whether the hot hand exists. Say someone's really hot for a certain, period of time and they can't do anything wrong. A basketball player would always, shoot and score. The quarterback would have amazing games on the run. And there's a big kind of argument in academia about whether or not this hot hand exists. So this is basically just an empirical way of looking at this using basketball data. So, and it basically does this by building lots of different regressions. For example, here we have a regression for, and this isn't a standard regression, this is a probability regression, but we've got one to predict the shot difficulty. We've got regressions to predict whether people make a shot or not. So we have this wide range of regressions, and I'm just going to kind of summarize some of the results of this. Note where it says dummy, this is just how we deal with qualitative variables in regression, i.e. we have variables for 3 of the 4 quarters, and these are dummy variables. We talk a little bit about, the book talks a little bit about this, talking about categorical variables. So we have these kind of qualitative variables for shot location, shot category, whether or not it's a fast break or not. I've no idea what a fast break is, but whether or not it's a fast break. And then we have the kind of the ratio scale variables such as the distance of the closest defender, the angle of the closest defender. And then we have some interactions. For example, the quarter time score differential. Obviously, the behavior is slightly different in the fourth quarter when the scores are very close, and in the fourth quarter, when there's like a 30, 40 point differential, and you know that one team's already won. And there's also some effects from the players as well. Then we define this kind of hot hand. Now, the reason we need this measure in the previous slide of shot difficulty and whether the probability, your chance of making the shot or not, is we need to define these metrics. So the simple heat is, your actual percentage shooting, how much you got over the past 10 shots. But the complex heat is how much you actually got over the last 10 shots minus expected you would get based on the predicted shot difficulty. And the idea here is that simple heat is not a good measure because somebody might just take, if they were, might just take very simple shots all the time. They'd have a high percentage, but it doesn't mean they're not actually doing well. The complex heat says, how much better you're doing than would be expected given the average difficulty of the shots. And so here's our little regression model. This is pretty cool. We will ignore kind of 3 and 4 because these aren't really, this is basically the probability of whether the same shooter, somebody takes shots twice in a row. And this is kind of, the predicted make of the shot. But let's just kind of look at these 2 measures, which are the important ones in standard regressions. So we have the shot distance, how far you shoot from. Now, this is based, and we're using the measure of complex heat from before. So this is we're predicting the shot distance, and heat has a positive coefficient. So and you can see that it's highly significant. We've got p is less than 0.01. So we can say that heat has this positive effect on shot distance. So you've got a high level of heat, you're doing really well, you're more likely to go for further away shots. So this is a measure that do you believe the hot hand exists? And the R squared is 0.296. You're saying, whoa, that's not particularly high? Well, in this context, it kind of is, because we're kind of thinking our kind of null hypothesis on this is that, heat doesn't affect shot distance, and a lot of things go into shot distance. So we can't expect, the hot hand to be, account for all the variation in shot distance. So a lot of regressions, the R squares are quite small because the effects are relatively incremental compared to other factors. And this is a defender distance. And we find that this goes in the opposite direction to heat. And again, this is highly significant. So if you're a very hot player, this basically means the defenders come close to you. The defenders hone in on you. If you're like LeBron, that's probably the only famous basketball player I know, or the guy from because I lived in Milwaukee, the guy from the Milwaukee Brewers. Those if you're one of these incredibly important players, the defenders really focus in on you and get close to you. So that's, do the players believe in the hot hand? And then, does the hot hand exist? And again, this is not kind of a traditional linear regression, but we'll just go through this anyway. Okay, so we have a base model here. The base model that doesn't incorporate shot difficulty is not significant at all. You see here the one variable we have the heat variable is not significant. Now we have two models here that we have shot difficulty. But what we call shot difficulty is the general probability of making the shots, with kind of the the opposite of shot difficulty. So the probability of making the shot is positively related to how easy it is to make the shot. That's kind of our measure from before. So that's kind of almost common sense. But interestingly, we add our heat measure. So the simple heat measure, actually accounting for difficulty, we're actually, if we have high simple heat, we're less likely to make the shot. So people with high simple heat, maybe they're not doing very well, so they resort to very safe, easy shots. Now the key complex heat metric, which is the probability of making above expected, we can see we have this model here, and we see the probability of making both incorporates the shot difficulty, the opposite of shot difficulty, and the complex heat, and both are significant. Though the complex heat is a little less significant, it's only significant to less than 0.05. So we have some evidence that complex heat actually, if you're on a run, it improves your ability to make the shot. Okay, so that was just for me kind of a simple example there of just like incorporating some regression models in an actual kind of interesting sports analytics kind of problem. My second little example, and this is kind of related to the work in the chapter where we're looking at different kind of different functions for regretting and seeing which is the best. This is just some work I thought was interesting. I did from examining viral video viewing patterns on YouTube from a while back. And what I did was I fit different functions to cumulative video views. I fitted a negative exponential function. And this is basically where we start off with a lot of views and then that popularity declines. So imagine like a famous artist like Taylor Swift has a huge inbuilt audience. So the first day her video is released, it gets lots and lots of views, and then that slowly declines. I look at these kind of logistic functions, and I'll show you the format in a minute, where basically we start off slowly, then we build to a peak as we gain viral traction, and then our views kind of slow down. And then I use the general polynomial functions as none of the above. And once we'd fitted all these, we looked at, the videos that were best fit with negative exponential. We looked at these kind of videos that had the best delayed viral pattern. And then we looked at kind of polynomial as like, it doesn't really have a pattern. It doesn't fit any of the above. So these were some famous YouTube videos going back quite a lot. This was done quite a while ago. And you see these were the best fit with the logistic, and the one above it got knocked off, but this was like the Gompertz and logistic function. The Gompertz is basically a slightly smoother logistic function. We also kind of incorporated kind of a single linear trend polynomial to add to the logistic function, because we still get views before and after the variable period. So this one here is kind of almost perfect. We start off with linear views, then we have this viral period, and then we go back to linear views. Same here, but our viral period starts, about 5 days after the video is released. This one's a little bit less obvious, but this is a good one here. We see we start off here with linear views, then we get this viral period, and then we get more linear views. Then we have our negative exponential. So we have like a massive kind of views at the beginning, which then slows down to linear, and kind of the same for these. And then these threes are none of the above, basically no pattern above. And then we kind of looked at this in the context of popular YouTube channel, and we found that, most of the channels, they got a lot of these kind of, delayed virals where we kind of like slowly built buzz about videos at the beginning of the channel. And once the channels had inbuilt audience, then we kind of had more of these, negative exponential, where they had a lot of initial views, and then this kind of slowed down over time. So it's interesting, some of the channels, they start off all with a lot of these kind of delayed viral, and as they build their audience, then they get more of the negative exponential. But they still have a fewer, videos that have kind of viral takeoff, as we get further through the video, which would help them build the audience. And you see, this is a classic example of Jenna Marbles. I don't know if she's still actually going. This is from a long time ago. Again, a lot of delayed viral and neutral polynomial videos, but once the audience was built, didn't get too many more members from the new content. And then slowly you see that the views went down and there were no more delayed viral videos. Where prank versus prank, you see actually built viewership over time, and it maybe built them with these new kind of viral videos. And a few more. We have our friend Taylor Swift. It's a little bit hard to see because this is a commercial channel, but we see we have some, videos that gain traction. Remember, there's a lot of interaction with the types of media with Taylor Swift. She's not just a YouTube channel. And then we have some British ones here, Thatcher, Joe, and Zoella. And then the Simon's Cat cartoons. And again, we have more viral videos towards the end, and then to the beginning, and then we have more of the kind of, we've got an inbuilt audience towards the end. So I just thought that, again, that was kind of an interesting little example of how we do some of the functional fitting that was mentioned in the chapter. Okay, so that's it for the moment, and I'm going to give a video with a simple example and also the usual Excel videos.